Okay, it's recording. Because my phone is over there for the recording, can anyone tell me when it's time to start?
Do you want me to adjust the clock?
Oh, you adjusted the clock?
I can try.
No, it's not.
No, do you want me to?
Can you?
I can try.
That would be great.
I can try.
Ooh, there's a radio bot with Astro? Yeah, that's cool. What do you guys do? No, we're like doing like radios stuff. Like this first slide is like also the processing, but now.
Oh, no, you can't reach it. Don't bother, don't bother.
Oh, yeah.
The safety issue about that.
So there's six sections, radio. Okay, there's three.
If you could just tell me when to start, and maybe 5 minutes before the end of lecture.
Okay.
Any questions on stuff so far? Everyone signed up for the piazza? Good, good.
Could you explain the gradient after we use the gradient operator to act on the annihilation operator, and then after on the zero state? Can you explain that again?
I didn't understand the question.
Can you explain this again? And so is there any meaning to the conversation of the gradient after the operator and annihilation operator? Or
From Bose.
They don't read, they don't give
It's like a paper tablet.
because it doesn't so it's not they wasn't adapting entire class. So they don't use that
yeah, maybe I want to ask, this operator act on the phi or act on this act on phi.
act on phi, yeah.
Yeah, but could we think is similar? Act on if I write the gradient here, that
It doesn't act on because the spectrum state doesn't depend on this.
So this year,
Yeah.
It's not zero in the sense that it's going to act on X. But your question is what? When you act on the factors, that's zero.
Yeah,
The factor state doesn't
I
always
was
be one
looking
position.
at the master, but I didn't.
It's empty everywhere.
okay, so this act on another thing.
Yeah.
The unit when we change the integrate, yeah, well, we have to the values. I checked this like it's not here. The side has a shape of.
That's correct, that's correct. So it's not equal, it's factor of equal and alpha.
There's a difference.
Yeah, but I didn't care because the only thing I'm asking you to do is to make sure that it's an eigenstate of the
Oh,
but you can be right, so this is factor.
Yeah, after it's like smaller distances, right? Like, you have pieces like, they look big and all.
Which university are you?
Let me explain that. Okay, so let me try to explain it.
Theoretically, it's like
Okay, all right. Okay, let's get started. So some of you asked questions about the midterm exam, and I intended to make it an open book, open note, but some of you also complained that there's not much space on your chair. So do you prefer to have it take-home?
Yeah.
You do? It's going to be sort of why such heavy homework? Because it's going to have a double weight. And you're supposed to do that in a week. Would that work for you?
Yeah.
Okay. Then some of you also said that most of the midterms tend to be in the mid-March, late March. So I can try to schedule it in early March to avoid as much conflicts as possible.
Or after spring break.
What?
Or after spring break.
After spring break?
Yeah.
You wanted it in April instead.
Yeah.
That's kind of late.
So that'd be a best dress for the final.
Here's another thing, because some of us also take 137B, and the 137B, the final exam, the period of the final exam is kind of overlapping with yours. So I think probably take home would be easier for some of us.
So the final exam is
The
overlapping?
final exam,
That is theoretically not possible, right? Because
it's
10
possible, but
possibilities.
it's kind of a rush because the gap between your final and the 137B's final is just like an hour or half an hour.
It's
And
30 minutes.
They're on the same day.
And also,
But no overlap.
They're not overlapping. They leave us only 30 minutes gap.
Yeah, but that I cannot avoid. Because campus actually decides that. I don't have any say.
there are people with extra time though. The people that like for the quantum mechanics exam stay there for like double the time. So how will it work for?
Yeah. So I think.
Oh, double the time?
Yeah, like there are
Yes.
people with disabilities.
Is that DSP accommodation?
Exactly.
So probably I don't know because you're
But
going to
even the
take
final
home
you said is a week's time, right?
Okay, I have to think about that. Well, there's still time for the final. So let's decide on midterm. So you guys all want to take home?
Yeah.
Yeah.
Okay. I'm okay with that. And when? So I propose early March, but you said you preferred
Oh, I know,
April.
I mean, whatever.
I'm afraid April is kind of late. Okay, so let me shoot for early March. I have to figure out which week is better for that purpose. But anyway, so I'm okay with takeoff, right?
Yes.
Everybody agrees? Okay. So let's get started with physics. And I see that one chalk here. Okay. So what I told you last week is that if you have this field theory Hamiltonian, V. This is the QFT Hamiltonian, which turns out to be completely equivalent to the multi-particle quantum mechanics with the Hamiltonian given by this. And you are checking this statement in the case of two-body state in your homework problem. But I did demonstrate that on the blackboard on last week, and I'm not going to do it for three bodies, it's just cumbersome, there's a lot of algebra, but this actually turns out to be true. So the rest of the discussion today will be based on the idea that they are indeed equivalent to each other. Yes?
Should the last term have two creations or just one creation?
I'm sorry?
Should the last
Sorry. Okay, thank you for putting that out. Any other questions? Yes?
The sign for QFT Hamiltonian, the V should have a plus sign, right?
Thank you, too. Okay, great. I really like this class that they point out all the typos on the blackboard. Any other questions? Okay, and this identification was based on this idea that you can define your multiparticle state with a capital psi instead of little psi by writing it in a way. X1, x2, xn, and you create n particles using creation operators acting on the vacuum state, and then smear it with a function that depends on these x's and also on time. So this is a definition of sort of generic n-body state in QFT language. But what you are showing in your homework problem is that this function here has exactly the same meaning as the multiparticle wave function in quantum mechanics because it holds the same Schrodinger equation that this actually ends up being the kinetic energy in the position space and potential energy. Now the xi is the eigenvalue, not operator in this expression. And this whole thing is now acting on this function. And this is the sort of standard Schrodinger equation you know and love from quantum mechanics. So this psi has the meaning of the usual probability weight. If you make a square of this, that will give you the probability of finding all these n particles at positions x1, x2, x3, dot, 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 xn. But using the same function, capital psi, you can define the state in QFT instead. And this follows the same equation, and that's what you're checking in your homework problem right now. So in that way, we now see that the sort of physical content of the theory is completely identical between QFT and quantum mechanics. And this is what actually we wanted, because the quantum mechanics, we know it works. It explains the data. It describes the nature at the microscopic level. So we're not trying to replace quantum mechanics, but we are just reformulating it in a way that's more versatile. And I will tell you in what way it's more versatile, because I can describe actually the Bose-Einstein condensate of cold atoms in a moment. But anyway, so this is actually same thing as quantum mechanics, but it's just bigger and better. So that's the idea. So what we like to do now is that now that we have this Hamiltonian in QFT, and we would like to understand the ground state of this Hamiltonian. And it turns out that when this potential is given by the chemical potential, just a constant, with mu being positive, so negative mu is negative, if you make this choice, it turns out the ground state of this Hamiltonian is not the vacuum state we have been talking about with no particles in it. It does have particles in the state, but it actually turns out to be the coherent state. So that's what we're going to see today. So that's the idea of where we're heading now. So any questions about where we're going? Is it okay? All right, so the first thing, we can solve for the ground state of this Hamiltonian in general. And just in case that you haven't actually recognized this, for most problems physics, you don't have exact solutions. And you have seen in quantum mechanics class that you can solve harmonic oscillator problem exactly, you can solve the Coulomb potential problem exactly, and so on and so forth. And they are actually exceptions than norm. Most problems in physics, you cannot solve them exactly. What that means is that you have to resort to some kind of approximation methods, or you have to actually put it on a computer, and rather than working it out algebraically and analytically, you just solve for the numerical solutions for them. So that's the case for most physics problems. For example, the Nobel Prize in Physics last year to Manabe was about the climate, and you don't expect you can solve for all this hydrodynamics and interaction between the air and the ocean on a piece of paper. You really have to resort to computer to solve that problem. And that's what he pioneered and got Nobel Prize for. So most problems you can't do exactly. So that's also true here. Just the case that you have this a collection of identical bosons interacting with this short-range potential given a delta function. That sounds simple enough, but you can't solve this exactly. Except when you take certain limits where you can have some exact solutions, and that's the case we're going to talk about. So it turns out that this is the collection of identical bosons, like some atoms, and in experiments, typically they use the alkali atoms like cesium. So this is the gas of cold atoms. And we're talking about this delta function repulsive force when two particles come together. And this is already a problem you cannot solve exactly. It's a multi-body problem, and it's very difficult to work it out. But you can when interaction is so weak interaction is weak enough such that each of these atoms can go through pretty much every one of them without hitting any one of them on its way, meaning that the mean free path which is the distance each atom can go without hitting any other atoms on its way, is much longer than typical interparticle distance. So in this limit, you can sort of pretend that interaction is negligible. So in that limit, you can actually solve this question exactly and find the ground state. And in terms of these parameters in the Lagrangian or Hamiltonian you see on the blackboard, this condition turns out to be this. And I haven't talked much about sort of dimensionality of space so far, but when you actually do this problem in the examples, what we want, of course, is that the space is three-dimensional, because that's the space we live in, so this is actually three-dimensional. When you talk about the delta function, that's also three-dimensional vector delta function on the three-dimensional vectors. And all of these are three-dimensional integrals. This is also three-dimensional vector. And also the canonical commutation relation between annihilation and the creation operator has to be three-dimensional as well. So if you do this, then you can figure out what the dimension of this the interaction term is. So lambda has a dimension of energy and length minus cube. And this 3 is the 3 dimensions of our space. And that's because this potential energy, of course, has the dimension of energy, right? So this has dimension of energy. What that means is that this is energy times psi log of psi, psi log of psi. So this combination then needs to have the dimension of energy. On the other hand, psi log of psi has a meaning of the number density, because psi log of psi integrated now on three-dimensional space is just adding the number operator at each position for the entire space. So this is the total number of particles in the whole space. So that tells you that psi leg of psi has a dimension of L minus Q. And that's when I made a mistake. So it's actually plus 3, right? So that this lambda is a parameter in the Hamiltonian times psi leg of psi, that's number density with a dimension of L minus Q, has the unit of energy. So this parameter has this dimension. And then you combine that together with mass, you know its dimension, and potential energy, and I'm taking that to be constant. So that's a chemical potential, and it has a dimension of energy. And the only other parameter I have is h bar. And you try to combine them to find the dimensionless combinations of them. Then it turns out that this is a unique dimensionless combination you can build out of these parameters. So this combination basically characterizes how strongly coupled the system is. And when lambda vanishes, then you don't have this delta function repulsive potential among particles. So that would be just a collection of free bosons. So when this combination is small, definitely system becomes totally free and kind of boring and uninteresting, non-interacting. But as long as this is finite, the system is interacting. But when this combination is much smaller than 1, you expect the system would allow you to understand quite quantitatively because the system is weakly coupled. So that's the limit we are going to actually use. Then I already mentioned last week that we resort to the variational method, variational method, that you come up with some kind of ansatz which depends on some parameters, and then you compute expectation value of the Hamiltonian using this ansatz the state as a function of these parameters. And then when you minimize the energy with respect to these parameters, then your ansatz which solves this equation becomes a pretty good candidate for the ground state. And that is what I believe you have seen in quantum mechanics class. So this is what is called the variational method, because you vary your ansatz state with respect to the parameters. And the minimum of the energy is a good candidate for the ground state to a good approximation. So again, this is not necessarily meant to be exact, but in many cases, this is actually already a pretty good candidate for the wave function of the ground state. And here, I really wrote down ground state in words here, because this zero state may not be the same as the zero state here, which is the vacuum state, which was meant to be a state that is annihilated by annihilation operators, psi, and this state may not be that. So in this ground state you come up with, it may not necessarily be annihilated by annihilation operator. So the vacuum state and ground state may be different. And of course, that's exactly what we want in the end, because we are looking for the ground state of the system of bunch of atoms, rather dilute, but nonetheless interacting. And what we would like to know is what is the ground state of that interacting system. So that's what we would like to actually do in terms of solving the ground state of the system. Okay, any questions about this? Is general idea okay? So it turns out that when this combination, which I just erased, let me write this again, when this combination is much more than 1, it turns out that you can, I'm not going to show this on Blackboard, but it turns out that psi you obtain from variational method, variational method, is indeed the ground state up to corrections in power series of this bracket. So in the limit where this combination is small, then it turns out the variational method gives you the exact ground state, where this variational ground state is given by this is the vacuum state. And this is just the extension of the coherence that we talked about in the case of harmonic oscillator. So what we did in your homework problem last week is that coherence state was given in terms of complex parameter f together with the creation operator acting on the ground state of the harmonic oscillator. And there was some normalization factor, and I'm not actually care about normalization factor today, but this was the definition of coherence state. And we have discussed how this actually ends up being the minimum uncertainty state, and then that would really resemble the motion of classical particle with minimum uncertainty in delta x and delta p, which just keeps circling around this big circle, which means that it really shows sort of motion like a pendulum, the x keeping going back and forth. When x is the maximum, the momentum vanishes, basically it stops. When it swings down, then picks up the speed, and then it goes to the other end, it stops again with zero momentum, and come back at maximum speed and so on. So this motion you could reproduce using the coherence state as a solution to the Schrodinger equation of the harmonic oscillator. So this is what actually resembles sort of a classical motion of a harmonic oscillator. So what we're doing here is just QFT analog of it. Once again, I have the exponential of the creation operator, psi dagger. And instead of summing over multiple harmonic oscillators, if you like, I have now integral, summing over the entire space instead. And then this state is actually an eigenstate of the annihilation operator, which is just given by this coefficient in the exponent, f of x. And in particular, we will be interested in a situation where ground state is homogeneous, it doesn't depend on x at all, so this f of x becomes just a constant throughout the entire space. But the idea is exactly the same as the coherence state in harmonic oscillator, which was an eigenstate of an annihilation operator. If we have multiple harmonic oscillators, we just put index I, and that index I now becomes the continuous index of position in space. So that's the definition of the coherence state in QFT now. And this is very weird notion, as you see immediately, because if you expand this out in Taylor series, you are summing over states with no particles. That's a vacuum state when exponential is 1. Then comes the first order psi dagger, which contains 1 particle in it. Second order psi dagger that will contain 2 particles in it. So you are taking linear superposition of states with different number of particles in your system. And that's something you can never do in quantum mechanics. As I emphasized already on day 1, quantum mechanics uses the wave function, as we talked about somewhere over here, with fixed number of arguments which correspond to fixed number of particles in your system. You can never change that. But in QFT, your Hilbert space is much bigger, which contains sub-Hilbert spaces with different number of particles in it. Now we're taking advantage of that idea that you can take even the linear superposition of states with different number of particles in your Hilbert space. And what I'm going to claim is that this actually turns out to be the ground state of this Hamiltonian when this combination is small enough. So what I would actually do now is to use this state, which is an ansatz, and compute the expectation value of the Hamiltonian, just like in the standard variational method in quantum mechanics, and then how we can minimize it to obtain the candidate for the ground state of the system. And it turns out that it's actually kind of non-trivial. So that's where I'm going now. So this actually looks like a strange thing to do because you have just got to the idea. If you do the QFT, you start with some kind of field at the classical level of Lagrangian Hamiltonian. When you quantize it, you get particles out because the field operator is actually creation relation operators. So you started with a wave, kind of, and you got particles out. And that is actually completely equivalent to standard quantum mechanics. But now I'm actually going one step further, that using now this QFT language, you can understand the system you cannot describe in the standard quantum mechanics. So that's one step further. So you first understand this quantum mechanics and QFT are the same so far, but using QFT, now you can solve the problem you cannot in quantum mechanics. And that's what you're just about to see. Thank you for waiting.
I have a question. With the variational method, we usually we make a guess for the wave function, and then we compute the energy.
Right.
And then we know if our guess was a good one, comparing the energy with the experimental data.
Right.
Is this what we are doing? So we are also, like the reason why you say that the coherent state is a good state is because someone else did the experiment and show that the energy that we compute is the same as the one.
Well, that's certainly one way of seeing why this is a good thing to do.
Okay.
And there's just purely also theoretical way of seeing why this limit gives you this coherent state as an exact solution to the system. And I actually postponed the discussion for now.
Okay. Sure.
But anyway, so that's something I try to explain later on. Yes?
Why does F being constant correspond to a homogeneous state?
I'm sorry, say that again?
Why does F being constant correspond to a homogeneous
So that's what you're going to see by looking at the minimization of the expectation value of energy in a moment.
Okay.
Any other questions? Okay. By the way, have you guys watched that video?
Yes.
Good. So that actually helps a lot. So we have the Hamiltonian up there. We have now the ansatz for the ground state, and we just go ahead and compute the expectation value. So this ansatz now is the coherent state, which in principle can have a position-dependent eigenvalue of the annihilation operator. And we compute the expectation value of the Hamiltonian up there in this coherent state. So let me write this out. And again, to avoid the classical notation, let me use y as the integration variable for the Hamiltonian. It's a dummy variable anyway. Function of y, and then I take the expectation value. But you can see that working out this expectation value is very simple because all the annihilation operators are now written on the right. All the creation operators are written on the left. So all the annihilation operators act directly on this coherent state. And just pulls out the eigenvalue by definition. So this psi of y is now replaced by f of y for the coherent state. And so it's here. So it's here. On the other hand, all the psi daggers act directly on this coherent state bra, which is just a Hermitian conjugate of the eigenvalue equation for this one. So if I take the complex conjugate of this, then this turns into and this the eigenvalue f of x is complex conjugated, just like in the case of harmonic oscillator. So all of the psi daggers now become f star y. And of course, you have to properly normalize the state, but assuming it is, then this just turns into simply substituting this f and f star into the Hamiltonian. So it's very simple. Yes?
Do the gradient operator and psi dagger commute with each other? Is that why we could...
I'm sorry, this one?
Yeah, do they commute with each other, the gradient?
This is the y derivative. And so I can actually take this derivative out of this.
Oh.
The state doesn't know about y, right? Because it's y is not an operator. So y derivative acts only on the field operator. So I can take this derivative with respect to y out of this. And then psi dagger y extracts the eigenvalue f of y star, and the derivative acts on that one. So that's the way it works.
So if it was x, we could not have done that?
This is the same. So this is dy, and I extract dy and just get the eigenvalue of psi of y out of the state. That becomes f of y, and y dependence is only on this eigenvalue. So he acts on that. So that's this term here. Is that okay?
Yeah.
Any other questions? Okay. So now I have a Hamiltonian as a function of this f of y. And if you're picky, this is a function of function, right? Because f of y is already a function of y, and energy is now written as a function of the function. So if you're picky, this thing is called functional. It's a function of function. It doesn't matter, it's just a word, but that's what you're looking at right now. So what we have to do then is to minimize this expectation value of energy with respect to whatever this f of y may be. So I take this expectation value, which is now written as f of y, with respect to f of y. And because this is actually a function of functions, people use this symbol delta instead of v, but again, this is a notation. And for simplicity, it's actually easier to work with variation with respect to f star. So what I do is to vary f star a little bit and make sure that it's stationary because it's supposed to be at the minimum. And then I have two factors that f star there, so if I take variation of one, the other one stays. That cancels the factor by half. And this is the point where I also use the integration by parts. So I let this derivative act on that one instead by dropping the surface term. So here I'm assuming that this is actually infinitely large system with infinite number of particles in it. and I don't care about the boundaries of the system. So then I can factor this variation with respect to F star out. And I demand that this is 0, so that it is at the minimum. The infinitesimal variation should give you 0 because it's at an extremum. So that's the idea of how to use Hamiltonian to write down the equation. If I actually started this with the Lagrangian instead, that's what you get, the Euler-Lagrange equation. We'll come back and talk about it later. But right now we are minimizing the energy, so we are minimizing the Hamiltonian. And then you find this equation you're supposed to solve. So now comes this weird idea. We are trying to understand what happens to this highly quantum mechanical system of very cold atoms interacting among each other. But it turns out that solving for the ground state of that quantum mechanical problem reduces to solving a classical wave equation. That's a really weird idea. Solving highly quantum mechanical system turns out to be solution to classical wave equation. And that's what you're looking at right here. And if you remember what we have done with the coherence state for the harmonic oscillator, that may not be too crazy, because what we have seen with this coherence state over here is this idea. That in quantum mechanics, you start with a particle, and you know it's Lagrangian. And Hamiltonian. Then you quantize it. With the canonical commutation relation, and you find that Hamiltonian is now the root operator, and you find eigenstates. And you find this wave function, which is given by this early polynomials times exponential, and these things have some kind of wave-like behavior. This is for the ground state, and this is for some excited states, and so on. And so every state looks like a wave now. So after you quantizing it, you get a wave. But then we learn that if you go to coherent state, and I believe I showed you animation on Zoom when we're still doing the virtual classes, the coherent state is highly peaked wave function. And this wave function really goes back and forth in space, and that resembles the classical particle. And this is really narrow because it corresponds to minimum uncertainty state, especially when you are far away from the origin, which means that if this amplitude of oscillation is big enough, then you can sort of ignore the spread of the wave function relative to the size of the motion. And that actually turns out to be very much similar to what you expect in classical mechanics. So what we have learned here is that you start with the particles, you quantize it, you get a wave. But if you go to coherent state, you get particles again, but not quite classical particles. because wave function really does have minimum uncertainty. And then you say this is actually a semi-classical particle. Which is meant to be that this is as classical you can get in quantum system. H bar is still finite. You're not setting H bar to 0. That is the classical limit. H bar is still finite. That's why there's still minimum uncertainty. But this is how closely you can ever get to a classical particle in a full quantum theory. And that's why we call this semi-classical instead of classical. So that's what we have done for the harmonic oscillator. Now, what we are doing with the QFT now is the QFT starts with this psi of x, which is a field. So in some sense, you are starting with a wave, some function of space. And with this wave, we have this Hamiltonian, which is that one over there. And starting with this one, you quantize it. And then understand that this can be interpreted as an annihilation creation operator. We have been doing this already for 2 weeks by now. And then you know that you have this vacuum state, one particle state, two particle states, and so on and so forth. So by starting the wave and quantizing it, you got particles out. That's what we did. And then further going to the coherence state in QFT, it turns out that wave and particle switched the interchange between QFT and quantum mechanics. You would expect that what you're going to get in the end is semi-classical wave. So by solving this wave equation, it is supposed to be a solution to the full quantum system. But the solution to this wave equation is supposed to give you a solution to the ground state, which can get as classical as you can be. It's still quantum theory, H bar is not 0, but by solving this equation, which is the analog of the harmonic oscillator equation for classical mechanics, you're supposed to get a wave function which swings back and forth like this one, which is supposed to be a solution to the quantum mechanical problem. That's sort of the 180-degree switch from what you have seen in quantum mechanics. But this is something you can do in QFT, in particular, when you have this interacting system. And as you saw in that video, when you go to low temperatures, each particle has its own spread in wave function. They are identical particles, but the spread of the wave function becomes larger and larger as you go to lower and lower temperatures, because as you go to low temperatures, energy is low, which means momentum is low. And when momentum is low, then uncertainty principle tells you that spread in space is large. So each particle starts to spread as bigger and bigger. So at high temperatures, you have particles sort of concentrated on their own positions. But at low temperatures, each particle starts to spread like this. And they start to overlap with each other. And they start to behave in collective fashion. So overall, they start to behave sort of together as if all these particles behave as if it were a classical wave. And that is supposed to follow this wave equation. So here, you see this complete switch between particle and wave. And of course, quantum system has this particle-wave duality. So it's always both. But because we are mere mortals, we don't grow up with quantum systems. What we see on daily life is only classical. So we have this idea that everything is either particle or wave. We can't comprehend what happens when it's both. So we have to start somewhere. And in quantum mechanics class, we started with the particles as a starting point of the discussion, went through this quantization process, and then you find that what you are looking at can be both. So in this semi-classical situation, it behaves almost like classical particle, but it's not completely point-like. It still has some spread and has minimum uncertainty. So that's a semi-classical particle, which is at the same time as a wave because it has a spread. In the same way, in QFT, you start with a wave because it's particle and wave together both at the same time anyway, so you can start with either one. So in QFT, you start with a wave, you quantize it, you get particles out. But when you look for the actual solution, it is supposed to be both anyway. And that solution is now described by this classical wave equation. So that's the complete switch from quantum mechanics. And this is something you cannot do in quantum mechanics because this is really a coherent state, which is a superposition of states with different number of particles in it. So now what we'd like to do next is just go ahead and solve this equation to find out what the ground state of this interacting system of the cold gas may be. Yes?
So I have a confusion. So from the table you've just written down, for the quantum mechanics point of view, we quantize the field, but what field to be exact are quantized? Like for quantum mechanics, what field are we quantizing? And for quantum field theory, like the treatment of quantization, what kind of field are we quantizing? I'm not completely clear.
Yeah, I'm not sure I got the question.
Okay. From the left-hand side, we have quantum mechanics. So we do the quantization, right? But the quantization of what field, is it equivalent to the quantization of the certain field in the quantization treatment of quantum field theory?
So it's the same, at least formulation. So in the Lagrangian, I have this half mx dot squared, and definition of P is always derivative of the Lagrangian with respect to time derivative of whatever variable you have. And then you find that this is mx dot. And in QFT we talked about so far, Lagrangian was psi star IH of psi dot minus this thing. So when you take the derivative of Lagrangian with respect to psi dot, that's IH of psi dagger. That's why you end up with this canonical commutation relation. So what we're doing is exactly the same procedure. And if you ask me why this works, I don't know. This is purely classical mechanics, and somehow mathematicians and physicists in the 19th century came up with this reformulation of Newtonian mechanics using Lagrangian Hamiltonian. They didn't have to do that because they already had Newtonian equation of motion. That's all you need to solve. But somehow they wanted to rewrite Newtonian mechanics with this idea that Lagrangian is fundamental, time integral of the Lagrangian is the action, and principle of minimum action is what reproduces Newtonian equation of motion. And so they probably felt that that's one step higher than just Newtonian theory, because you can derive Newton's equation of motion from Lagrangian action. And somehow that idea turns out to be really crucial when you want to quantize a system, because what you do is, starting with the Lagrangian, you identify the canonical momentum and set up this canonical commutation relation, and that defines the Hilbert space, where you try to solve for the eigenstates of the Hamiltonian, eigenstates of the momentum operator, and so on and so forth. Somehow that idea worked. And I really don't know why it did. Because 19th century, they didn't know about quantum mechanics. But somehow they had this foresight of reformulating Newtonian mechanics in such a way that you can go ahead and do this quantization thing on top of it. And that actually led to quantum mechanics, which we know works. So what we are doing here in QFT is just follow the same process. Instead of talking about Lagrangian for particles, we now have Lagrangian for waves. And go through the same process and do this quantization. You find Hilbert space. You have seen that already. Hilbert space contains the particle state with no particles. The vacuum state stays with one particle, two particles, and so on and so forth. That's your Hilbert space. And then you're trying to solve for the ground state of the Hamiltonian, just like we normally do in quantum mechanics. And we have to play this little trick that we rely on a variational method to find the ground state of the system. But that requirement for solving the ground state ends up being this classical field equation at the end of the day. So that's the idea. So we are not doing anything different from what we have seen in quantum mechanics, just the starting point is different. Yes?
I guess a similar question is, what is that psi of x? It's not the same as the annihilation operator.
No, this is the annihilation operator.
No, I mean the wave that you're talking about.
This one?
No, the wave.
Wave,
Psi of
about
x.
the wave. Psi.
Yes?
Psi,
Yeah, is that
what
not
is
the
that?
operator?
Oh, so this is at the classical level before quantization. So psi of x is just some function of space which follows some equation. So that's what I'm saying as a wave. But when you quantize it, it becomes the annihilation operator.
Oh, is that a probability wave or is it just any function?
Any function of x at this stage.
Oh, okay.
So in the same way that when you're talking about particle, x is any function of t.
Got it, okay.
Now, how do we understand that the psi x is a wave?
Well, a wave in the sense that depends on space.
Okay.
So
But we
x
can
of
also
t
understand it as a
follows a
field.
trajectory. So x and t. So it always localized at a position in the space. But psi of x is something that is distributed over space and which may change the function of time to like that and this and so on and so
Also,
forth.
the psi x, the original you written psi x, then that psi x should have been this psi xt.
That's right, right. So this is actually in this Lagrangian. And from this Lagrangian, you can beat off that psi and psi star are canonically conjugate to each other. And then you go ahead and set up the canonical commutation relation and find the Hilbert space for it. That's what you have seen already. 0 particle, 1 particle, 2 particle states, and so on and so forth. And you have also seen that this way of formulating it is completely equivalent to quantum mechanics. That's something you have seen already. So even though starting points are totally different, they mean the same thing. But now you go ahead and try to find out the ground state of interacting system. So initially we talked about just the collection of free particles. But now they are interacting. It becomes a little bit more difficult problem. But at least in the limit where this interaction is small, which is gone now somewhere, then it turns out that solving this equation actually does the job of finding the ground state. So the next thing is just let's go ahead and do it. So that's where we are right now. Yes?
Just to make sure that psi star and psi dagger and psi are different in the Lagrangian, right?
Yeah, they are different.
psi
So
dagger.
psi star was just complex conjugate, but after quantization, psi becomes an operator.
Is that still the same wave that we defined?
It's the same thing, and just that complex conjugation doesn't mean much when you're talking about operator, so I'm just writing as a Hermitian conjugate instead.
Wait, so we defined the psi dagger to be an operator.
Yeah,
But
both
your,
psi dagger.
but your
operator.
original psi was a mathematical function.
Yeah, initially it was just a mathematical function.
So how did it become an operator?
Well, in the same way that x of t was just a function of t,
Oh, I see.
but becomes an operator when you do quantum mechanics.
Got it.
So you're already used to this idea. So now I'm applying the same idea over here in QFT.
Got it.
Could you explain
Yes.
how do we get the wave formula, the partial f over partial psi dot is equal to I h bar?
Well, it just comes from this term in the Lagrangian. I'm sorry it's written very tiny, but this is psi star I h bar psi dot.
So how did we get this Lagrangian?
And that's what we did when we actually did the harmonic oscillator. And then wrote the Lagrangian for the harmonic oscillator using A and A dagger. And then promoted it as an annihilation correlation operator as a function of the position. And then took the continuum limit. So this was there all along.
So from the classical harmonic oscillator, how do we get the X bar term?
If you use X and P, of course, this is the canonical commutation relation, but you can rewrite this X Lagrangian using A and A dagger, and that turns out to be A star IH bar A dot minus H bar omega A star A. Because X is basically X plus IP, the A is basically X plus IP, A dagger is X minus IP, so I can rewrite X and X dot using A and A dagger. If you substitute that in, this is what you find.
Oh, thank you.
And I think that, I have that in lecture notes on the harmonic oscillator. So if you look at that, you can really show that this Lagrangian is the same as this Lagrangian. Then we promoted it as a creationalization operator for a site on a one-dimensional lattice. Then took the continuum limit, so this became integral instead of a sum with a factor of d to the 1/2, so this becomes psi. So from this term, I get psi star IH of psi dot. And that's how I know that this is the correct canonical commutation relation. Okay? Yes?
How do we, so do we interpret the Bose-Einstein constant to say as the collection of non-interacting bosons to be like, one wave, or is it a collection of each of the particles' waves that are just exactly overlapping?
So that's coming soon, so let's wait for that, okay? Any other questions? Yes?
Could you explain what happened to the lambda, lambda over 2 when it became lambda?
Say it again?
Like in your Hamiltonian, when you plugged in the variation, why did it become lambda? I didn't understand that.
So do you ask why factor 1/2 went away?
Yeah.
That's because I'm taking a variation with respect to F star. Here I have 2 powers of F star. So taking variation of 2 powers is 2 delta F star F star. Okay? I saw another hand. Yes.
You mentioned that the 2 columns on the right hand, you say that we go from classical notion from particles and waves into the duality of particle wave duality.
Right.
And we know that essentially what is a wave, what defines it's a wave, it's the coherent superposition modality. Right?
That's right. So that's coming. So I haven't explained that yet.
Yeah, I just want to quickly talk about how do because the semi-classical particle is a coherent state. Why would they name it as coherent? Is it relevant to the?
Yeah, it's coherent because it really is coherent. So what I'm going to talk about later is that when you have 2 collections of this cold gas of atoms, and when they overlap with each other, there's an interference pattern. They are fringes. Even though it's a collection of particles, you see the fringe pattern. That's why it's coherent. Okay. So you see that later. Yes?
So the particle and wave duality is basically because of the introduction of knowing that there exists a coherent state, or that we can have the same solution when it comes to solving the wave equation, but actually it's a highly particle.
Yeah, that's a good question. So as we talked about in the case of harmonic oscillator, coherent state is the minimum uncertainty state.
Yeah.
So this is a state which can be both as much as a particle as possible and as much as a wave as possible at the same time. So this is the state that would exhibit the particle nature and wave nature as much as possible at the same time. So it turns out that this is also that kind of situation. And so that's when you see the particle wave duality as much as you can. And in most other states, it may look more like particles or more like waves, not both together. So this is the way you can see this duality idea very clearly compared to most other states.
Then, because we obtained the box equation, knowing that the dimensionless factor is small enough.
Right.
But if it is not small enough, then we
That's right.
That the wave particle duality no longer exists.
It could still survive depending on the circumstances. So when this parameter I talked about is not small, then you certainly have to worry about corrections away from the coherent state. It may be a good approximation, but you still have to put corrections on top of it to understand the system quantitatively. It may still be qualitatively okay. It turns out that in the case of the superfluid helium, which is actually one example of such a Bose-Einstein condensate, that parameter is not small, but doing this still gives you a qualitatively good description of what is called the superfluid. So that's the fluid of the liquid helium that flows without viscosity and does all kinds of weird things. It can climb up the wall of the beaker and spread out on its own. It seems to defy gravity. It's a very strange object, but nonetheless you can talk about it using this wave equation. So it's still qualitatively a good description, it turns out. So in many cases of physics, if you have this big parameter space, and typically Schrodinger coupled systems are in between, where you don't have a good tool to solve it exactly. So whether you start here, where you can solve exactly, and approach it over there, and hope that still qualitatively is a good description. Sometimes you may have to start here, or over here. So real problem cannot be solved exactly, but you try to find a limit where your description is qualitatively good enough that you think you can understand the system. So which limit is a good description for your system depends on what you're looking at. But trying to come up with this good zero-to approximation is really the key for any physicist to understand the system. And so in the case of the standard electromagnetism, in talking about classical electromagnetism is typically a good approximation. That's why we use it. But when you go to photoelectric effect or quantum scattering, that's no longer good enough. Instead of talking about photon, becomes a better description for those processes. The classical electromagnetic wave wouldn't do it anymore. But if it's really a particle, if you ask the question, well, not quite, because it's also wave at the same time, but starting with a photon as a particle is a better description in that limit. So you always try to come up with some limit where your simple understanding is good enough, then try to add corrections on top of it to fully understand your system quantitatively. And that's sort of the heart of physics. That's what we do all the time. Because most systems cannot be solved exactly. And it's also very counterintuitive in our mind because it's wave and particle at the same time. We don't have a good intuition for it. But nonetheless, you can come up with some description by starting somewhere, which turns out to be a qualitatively good description. Okay? Any other questions?
So it's true that the coherent states aren't eigenstates of the Hamiltonian.
Yeah, so in the limit where this parameter is small, which I erased, it turns out to be that this is actually the exact solution to the system.
Okay.
Okay, so let's just go ahead and solve this for now. So what I claim is that the system of large number of identical bosons which interact repulsive interaction turns out to be the same problem as solving this equation. And set up the coherence state for it. Now, we look at two different cases. When chemical potential is negative or positive. And this is a nonlinear field equation because this is linear in F, this is linear in F, but this is cubic in F. And solving nonlinear field equation is typically not possible, even at the classical level. You might put that in a computer, but most times you can't solve it. But at least in some cases you can. And when mu is negative, the only simple solution I can come up with is this. And that obviously satisfies this equation. Every term vanishes. And when you remember the f equals 0 means that this is the eigenstate of an annihilation operator. When f is 0, this is annihilated by annihilation operator of every position, which is nothing but the vacuum state we talked about. Which actually makes sense. Negative chemical potential means if you try to put more particles into the system, you lose energy. So looking for the ground state, it's better off not to have any particles at all to minimize the energy. So in the end, you don't have one. So this looks sort of trivial and uninteresting, but at least it makes sense. And indeed, this is the ground state of this Hamiltonian when chemical potential is negative. But something more interesting happens when chemical potential is positive, because when chemical potential is positive, by putting more particles in the system, you may gain energy. Meaning that when you try to minimize the energy, you want to have particles in it. And that's the more interesting case. And then you can try to look for the solution. Again, this is a nonlinear equation. So in general, you can't solve it. But you can at least look for a solution which is homogeneous in space. Namely that f is a constant in space. So in that case, only these things have to be solved. And immediately you see, you can graph the f out. Then you find multiple solutions this time. Of course, f vanishing is a solution. But you have another solution, now that mu is positive, that you can balance this negative mu against this lambda f star f, so that f star f is mu over lambda, which is now positive. F star f is the absolute value of the complex number, so this is definitely positive, semi-definite. But now that mu is positive, you can find a solution. So now you find two kinds of solutions to the system, whether f vanishes or f satisfies this. That's when it's useful to draw a graph for the potential energy and this is a complex number, but let me just draw it for the case of when f is real. When f vanishes, that's 0. And if chemical potential is negative, then this coefficient is positive, so it starts to rise quadratically. And when f becomes large, eventually quartic term becomes more important, so it steepens up. And you find potential like this one, and lo and behold, origin, where f vanishes, is the minimum of the energy. But when mu is positive though, it again starts out at the origin, but quadratically it starts to go down. And only after a while, when f becomes large enough, the quadratic term starts to pick up, and potential rises like this. So looking at a graph like this one, you immediately conclude that one of the solutions where f vanishes is an extremum but not the minimum. It's a maximum instead. The minimum is over here or there, where f doesn't vanish, which satisfies this requirement in the end. And that turns out to be the solution for the ground state of the system. So the ground state ends up being a coherent state where the eigenvalue of the field operator is given by a solution to this one. And I remember actually looking at some newspaper article that NASA was trying to design an aircraft, and they are trying to actually maximize the range that it can go for long distance for a given weight and amount of gas and so on. So engineers worked very hard to come up with the parameterization of the range of an aircraft as a function of material and shapes and all that stuff. Took the first derivative, set it to 0, solved it, and ended up minimizing the range. So you have to be careful when you actually solve for the extreme of some equation. You want to be sure that you're looking at the minimum instead of maximum. So that's what you have to do. So f star f is actually finite. And of course, f is actually complex. So if you actually rotate this picture around like this one, you find a trough. And this thing is actually like this. And you have actually infinite number of solutions along this trough, where f is given by square root of mu over lambda times some arbitrary phase. So that's the solution of the ground state, it turns out. But this is still not that interesting, because everything seems to be static. And when you look a little bit further into this equation, you also find that not only this solution with a static phase is a solution, but you can also find a solution which does depend on space and time, but the phase given by mvx minus half mv squared t. This is a solution to that nonlinear field equation. So even though I didn't write the time derivative piece in it, time derivative piece is IH bar f dot, as you can get from the Lagrangian by taking variation with respect to star. And you will definitely get a homework problem on this. So I give you the equation, and you are supposed to verify this in the solution. But the difference between this one and that one is this describes everything is homogeneous, so these cold atoms just occupy the entire space with no notion of time dependence in it. This one actually describes the flow of this gas in one direction given by this velocity v. And now comes the question about the coherence. If we have two of these, and each of them is approximately very much extended. So this one is described by f1, which is the square root of mu over lambda e to the I h bar mv1x. And this one is described by f2, but if you have two of them overlapping with each other, you add them. Take absolute square to get the number density. You have to remember that this is an eigenvalue of psi. Psi dag of psi is the number density of particles. And if you do this one squared just gives you a constant. That's the number density of the first gas. that one gives you the Nernst number density of the second gas, but there is the cross term between, which goes like a cosine of h1 over h bar m v1 minus v2x minus half m v1 squared minus v2 squared t. And this x dependence tells you when they overlap, you see fringes. The idea is that you're looking at the collection of atoms, particles. But when they overlap, you see a fringe pattern. And this is not the fringe pattern you heard about in double slit experiment in quantum mechanics. Because in double slit experiment in quantum mechanics, each time you send in a particle and hit somewhere, and you see a dot. When you send a second particle, it goes somewhere, you see a dot. And by repeating it over and over again, you eventually see this fringe pattern. That's the idea, right? But here it's different. On one shot, when two gases of the atoms overlap with each other, you see a fringe pattern. It's not a repeated experiment, because this is already a solution as a ground state of the system for each systems. And when they overlap, there's already a fringe pattern, because this is actually already behavior of thousands of atoms working together, as you saw in that cool movie. So when you cool down the particle down to a temperature of like nanokelvin, then they start to overlap with each other, and collectively, thousands of atoms start to behave like a wave, described by this wave equation, and they show this fringe pattern as a whole, but on one shot. Not repeated experiments, but on one shot, you see this fringe pattern. And that's why these states are indeed coherent. So that's the idea of Bose-Einstein condensate. And now that I'm actually showing in person, I'm not showing any slides and data, maybe I should learn to actually use this one next time to show some data on this. But this is something people have really seen. And Dan Stadtbecker in the department is actually famous of working in the lab of the Wolfgang Keppeling at MIT, where they first produced this kind of BEC with cold atoms, and Keppeling got the Nobel Prize. I don't know why Dan didn't, but anyway, so that's how we know that the cold atoms really do show this kind of fringe pattern. Yes?
You asked me to remember you when it was almost time to finish the lecture.
Oh, over time?
No, you're not over time.
Ah, okay, sorry.
3
minutes, sorry. Thank you. Yes?
So like when we are solving for the equation, we assume that it is homogeneous in space.
Yeah, that's what I assumed, because
but the solution
I can't solve this equation in general.
Yeah, but the solution we comes up later, there actually involves x dependency.
Yeah, it involves x dependence, but still homogeneous in the sense that when you take f absolute squared, that's constant.
Yeah,
right?
but
because it's a phase.
I think it will give an extra term in the derivative term, like.
Yeah, but it turns out that when you actually plug this one into this equation, f dot pulls out this half mv squared, and this one here, special derivative, pulls out mv squared over h squared 2m, so they cancel.
But where the time dependence comes in, like.
Yeah, that's what I didn't show. So I minimized the energy today because I started with it from the concept. But when I go back to the Lagrangian instead, and let me actually write this in a big font. This is the Lagrangian, and time integral of this is the action. And principle of least action says you get the equation of motion by minimizing this. So I take the variation with respect to psi star. And then kind of 2 that is cancelled. Then doing the integration by parts, I add this on sun at the expense of sine. Then I can factor delta psi star out. And this thing has to vanish. That's the Euler-Lagrange equation. That's that equation up there. So when I start with the Hamiltonian, I didn't have time derivative, so that's why I only have the first term over here. But when I go back to Lagrange and do the minimization of the action, that's the least action principle, you get the Euler-Lagrange equation, which does have this time derivative in it. And once you do have it, you can find that this is actually a solution, which corresponds to a flowing Bose-Einstein condensate. Okay?
So, is it me?
Yeah, you.
Oh, okay. So can I say that we're not actually solving for the ground state of the system, but like we're approximating this state to be like a eigenstate of Hamiltonian and try to find its
Yeah, so that's something
time
you have
evolution.
done in the harmonic oscillator problem, right? So you solve for the time evolution of the coherence state, which turns out to be n to the I omega t times minus I omega t over 2. So here you have found this time dependence of the eigenvalue of the annihilation operator.
Is it like we're solving a time-independent Schrodinger equation? Is it the same idea of it? Is it the same thing?
No, it's not time independent. So if you have a time independent Schrodinger equation, the only thing you can get is the stationary state.
Yeah, so we leave all the time derivatives in that equation, right?
Yeah.
Yeah, so I think is the idea the same?
Yeah, so then you get just the coherent state without any time dependence in it, because you're looking for the stationary solution.
Yeah, I mean that.
But when you're looking for a collection of atoms that is moving together, then something depends on time, because things are moving. It turns out that going from here to there is just Galilean transformation from one reference frame to another reference frame. And I tell you on Friday how that actually works to give you this solution even without solving the equation, because everything is Galilean invariant. Okay? So that's, yes?
So experimentally, how can we like put a chemical potential to the...
Yeah, so that's an interesting question. So in the end, what you have to do is that first of all, you kick the atoms out of the oven, and then you put in a trap, typically magnetic trap or laser trapping. Then you have some kind of potential energy where you can collect a bunch of atoms inside, but it's dilute enough. Then you do all kinds of techniques to make it cooler, and this temperature has to go down to the level of nanokelvin. That's much cooler than the temperature of the universe, which is 2.75 Kelvin. But you can do that. And then you actually start to see that these particles have waves behavior, and they start to overlap with each other, and they start to collectively behave like a single wave of a collection of particles, not just individual particles. That's where you see the particles together behave like a wave. That's indeed particle-wave duality. And this wave behaves as if it is just a solution to the classical equation of motion, and they demonstrate this kind of coherence. So that's something you can do actually in the laboratory. So if you ask Dan, maybe he can actually show you how that works in his laboratory. And so that's really amazing physics. And that you can really see this particle-wave duality in the laboratory directly. All right, so I stop here, and we continue on from this point on Friday. Hopefully the recording worked out.
Yeah.